we will start the final chapter now. Okay, so you have dimensional analysis and scaling. In this chapter, we will learn several practical issues that we can use in real life. So first, we will learn dimensional analysis, which is a technique for gaining insight into fluid flows. And before we do either extensive theoretical analysis or experimentation, we can perform this to know what are the main parameters that will affect our um, uh, case, if you want, and how we can relate them through dimensionless groups. So this technique will enable us to extract trends from data that would otherwise remain disorganized and not coherent. What do I mean by this? So for example, if you are designing an airplane, okay? Of course, doing experiments on the real airplane will cost a lot. So to start with, will not go directly to the final model of the final prototype of the airplane. We'll build a small model. We can have it much smaller than the true dimensions. Okay, but we'll see what are the conditions to say that if we test, for example, in a wind tunnel on this model, what are the conditions that will allow us to extrapolate the result to the real case. So this is one of the main objectives of this chapter. We'll see how by performing dimensional analysis, we will be able to extrapolate results that were considered on simple experiments to much more complex real cases. Okay? And there are many such interesting dimensionless groups that we will go over in this chapter, like Reynolds number and Mach number. For example, you are already familiar with Mach number. We define Mach number as the ratio of the fluid flow over the speed of sound in this fluid. Okay, and we said that this number can help us into knowing if a flow is incompressible or not. Okay, if we can treat it as incompressible or not, because for example, air in general is a gas, so we treat it as incompressible, but in some cases as compressible. But in some cases, we can treat it as incompressible if the Mach number is smaller than 0.3. So in this case, the compressibility effect can be neglected. Okay, and the Reynolds number is a very famous dimensionless number, and it's used to know if a flow is laminar or turbulent. So it can help us to categorize the flow. Now, also we will, as we said, at the end, we will learn what are the conditions to extrapolate analysis from an experiment on a small model to a bigger scale, or the opposite. Sometimes if you have an application in the micro scale, you have very small dimensions, it's not practical to do experiments with very small dimensions. So you can build a model that is larger, where you can manipulate easily experimentally, and then extrapolate the result to the micro scale. Just you should pay attention that you have similar conditions. You should satisfy similarity in geometry, in kinetics, and we'll see all of these details at the end of this chapter. Okay, so this is in overall the objective of this chapter. Now, to start with, we have first, when we solve the Navier-Stokes equation, you remember when we end up with chapter 6, we said that Navier-Stokes relations are very complex, and solving them is not simple at all. They will require the development of a numerical technique called computational fluid dynamics. For example, if you want to solve for the flow behavior over this car, okay, you can do experiments, and you can do computational fluid dynamics analysis, and at the end you can draw profile of forces, of pressure on your car, of how the velocity field is doing separation around the car, etc. Okay, so to treat this problem, we have two approaches in general. The experimental one, if you want to perform experiments in general, you can take a small model car and fit it in the wind tunnel and measure desired quantities as frictional force, pressure on windshield, etc. And then we will see how we can extrapolate these results to the real case. Okay. And the other possibility is to use computational fluid dynamics, and then we can measure all of the parameters by just, we don't measure them, we do simulations, we compute them numerically. Okay. Now, in general, they combine the two approaches. They use experiments, and at the same time, they use CFD. Experiments can be used as validation for the CFD model. This means that I can make sure that my CFD is giving accurate prediction close to the experimental results. And once I validate this, I can conduct the parametric study on CFD. Okay. Now, so to start with, we will introduce the main flow scales, and we will introduce dimensionless numbers that are frequently used in fluid, and we'll give some famous examples of the use of dimensionless numbers and empirical data to solve complex engineering problems, like how to determine drag and lift coefficients that are very important in aerodynamic applications where you have motion of cars or where you have motion of airplanes, etc. So the first scale to take into consideration is the length scale. Okay, and the length scale is very important. It will give us an idea about the size. So you have in real life, you have a wide variety of sizes from the micro to the macro scale. Other important scales are velocity and time. So in any fluid system, we have mainly these basic scales are involved: length scale, velocity scale, and time scale. Okay, and each of these scales have a physical meaning associated with a certain parameter of the flow. And we can define, for example, any new variable function of these scales, as we'll see in the dimensional analysis. So the basic theory behind this chapter is that fluid forces scale with the size of the system. So if you have, for example, a large system, you expect to have on it large forces. If you have smaller systems, the forces will be smaller. But if you do the ratio, you will get similar ratios. Okay, so the ratio of forces between large and small systems is expected depend on the ratio of sizes. So you can relate ratio of forces to ratio of sizes, and then you will be able to extrapolate results on small scales to results on bigger scales. Okay. So for example, we can consider, let's say, if we want to perform an experiment, okay, to assess the behavior of a, let's say, of a the expansion of a gas, as you can see in this figure. Okay, here you have a very large scale. You can simulate this, okay, by using, for example, smoke generation, but at a smaller scale, but still observe the same behavior. Okay, so what you can do is you should determine what are the dimensionless numbers that are affecting your result. Okay, and then you can expect the plume behavior, the real plume behavior, from your experiment on a much smaller scale. Another very important example is the similarity between airplane flight and the insect flight. You can see here the difference in sizes, but at the end, the mechanisms are very close to each other. And when we come up with the design of airplane, we used a lot if you want, the mechanics of insect flight, because we profit from nature to come up with the design of the airplane. So there is a similarity in shape between the two systems, despite that both have very different scales. But for example, both have a body and two wings, and we can extrapolate a lot of mechanics from the insect flight to the airplane flight. So yet there is a striking difference in system size. Thus the fluid forces in the big plane must be much larger than in the insect, but we can extrapolate the result of aerodynamics on insect flight to airplane flight if we find the appropriate dimensionless numbers. Okay. So here, for example, as we were saying, we can perform a jet in a laboratory experiment that is of a few centimeters in height, while the real life jet can be 1,500 meters in height. But as you can see here, if you compare figures, the behavior is very close. So notice the striking similarity of behavior between the real life jet and the lab jet. The fluid dynamics are very similar in both cases. Yet there is a striking difference in size, and the forces in the big jet must be much larger than the lab jet. But at the end, the dimensionless numbers will be the same for both. This is why you will be able to extrapolate results from your experiments to your real life case. Okay? Any question on this? So, for example, let's say you want to perform experiment on an airfoil, okay? And you want to extend your experiment result to a bigger scale. The condition first is to have the same ratio of sizes. And this means that if the chord length in this airfoil here is 8 meters, and in the smaller one it's 0.8, this means that the ratio of, if you want big L over small l, is 10. Okay, so to have similarity in geometry, this ratio should remain the same for all other dimensions. So here, if you consider the span of the airfoil 40 meters on the big airfoil, you should have here, it should divide it by 10 also. Okay, so then you can say that you have a geometric similarity between the two. And to ensure geometrical similarity, the second condition is to have the same angles. Angles will not change, and the ratio of length should be the same for all dimensions in order to ensure that we have geometrical similarity. Now, for example, also here we can, if you want to, for example, find results about drag and lift on a sphere, okay? We can perform experiments on a medium sphere and extrapolate the result to know what will be the drag and lift coefficients on a huge sphere or tiny sphere or large sphere. The only condition, as we said, to extrapolate results is to have the same dimensionless number. And we'll go in detail over how to do calculations in this case. Just now we are introducing what we will do in this chapter. So let us start now with the first part, which consists on finding, if you want, the non-dimensional form of the equation. Okay, so if you remember in previous chapter, we developed Navier-Stokes relations, and we said that these relations are very important and in fluid dynamics, and we can have in some cases analytical solutions like flow between parallel plates, flow in a cylinder, in a duct, etc. Now, in general, these relations are in complex cases like cars and such problems. It's not easy to solve these problems at all, and you don't have analytical solution. So you go to experiments or to computational fluid dynamics. Okay. Now, to make the experimental result general and to make them, if you want to be able to extrapolate them to general cases, then we prefer to write all equations in non-dimensional form. This means that all of our terms should be without units. Okay? How to do this? So for example, in the following relation, you can check for the homogeneity of this equation. All terms have the same unit. Okay? If I consider, for example, del U by del T, I have meter per second for U, and for time it's second. So I have meter per second square, okay, which is the unit of acceleration. So if you check, you can check that all other terms will have the same unit. So for example, if you take now U del U by del X, okay, what is the unit of this term? You have meter per second times meter per second over meter, because X, the unit of X is meter. So here, if you simplify meter and meter, you get meter per second square, as expected. Okay. Now, for example, if you checked for this term, no need to do it for the other terms, because as you can see, it's the same form. You have the same form for this one and for this one. Okay. Now, on the other hand, for the other terms, you can check that G is a gravitational constant G. Okay, so it's equal. It has the same unit of acceleration. It's in meter per second square, so it's fine. Now, for example, for this term, okay, you have rho is kilogram per meter cube. So 1 over rho unit is meter cube per kilogram. For pressure, it's a force per unit area. So it's Newton per meter square. Okay, and always you can express Newton function of the other dimensions, because Newton is ma, mass times acceleration. So since Newton is mass times acceleration, the unit of it will be kilogram times meter over second square. Okay, so you can see here that by doing the appropriate simplification, kilogram and kilogram will cancel out. Here you have meter cube over meter square over meter will cancel out. So you'll end up only with the unit of meter per second square as expected. Okay, and finally, we can check that mu over rho times del square U over del X square has also the unit of meter square per second. For example, for the viscosity, maybe you don't remember what is the unit of viscosity. It's fine. No need to memorize it. You can just say the viscosity parameter is involved in which equation? In shear. If you remember, shear is equal to mu times del U by del Y. Okay. So, and we know that what is the unit of shear? Shear is Newton per meter square, and we can replace the Newton as we did now by m times a, so kilogram times meter per second square, and it's over meter square. So you can cancel if you want meter here, and you get just in the denominator meter to the power 1. Okay, and this is equal to mu. We don't know the unit of mu. We want to try to find what is the unit or what is the dimension, if you want, of mu. Okay, now for del U by del Y, it is meter per second over meter, so it's just 1 over sec. So now if you take second to the other side, okay, you will get that the unit of mu is kilogram over meter sec. Okay, so this is the unit of mu. Now, if we replace now mu, the unit of mu in this relation, so we have kilogram over meter second. Now we divide by rho. Rho is in kilogram per meter cube. So you have here kilogram and you multiply by meter cube. So first, kilogram and kilogram will cancel out. You have here meter and this is meter square. So you have meter square per second times the second derivative of u with respect to x square. So here you have u, the unit of u is meter per second. While here you have del x square. So del x square is meter square. So now what will happen is that meter square and meter square will cancel out. And over second will give you meter over second square. So again, we verified that all our terms have the same dimension. And if it's not the case, then we say that this is not a homogeneous equation, okay? And then we cannot use it in any system of units. If you remember when we considered in first chapters of fluids, we said that if you have an equation and let's say we replace g, for example, and if you want to use SI units, you should replace g, let's say, by 9.81. If you replace g by 9.81 in the equation, this will not make it any more general, because if you apply it in English system, it will not work. To apply it in English system, you should replace g by 32.2. Okay, so an equation to be general, we should be able to apply it in any type of units, in any type of systems. Okay, and this requires that all terms will have the same, of our equation will have the same unit, the same dimension. Okay, which is here the dimension of an acceleration. So now, what is the purpose now? The purpose is to transform this relation from terms with dimension to terms without dimension, so without unit, to be able to generalize it if you want and use it in any case. For example, if you do experiments on a smaller scale, so if you want to apply it on a bigger scale, then the only condition is to have the same dimensionless numbers that will figure out in these equations. Now, when we do the application, you will understand more what you are talking about. Okay. So, how to perform the dimensionless form of the equation? How to reach it? To be able to reach it, we should scale all our variables. We should normalize all our variables. What do I mean by this? For example, in these Navier-Stokes relations, let's say one of the important parameters is velocity, u. Okay, u has the unit of meter per second. If I want to define a parameter related to u that is without dimension, u star, okay, I should say that I can define u star without dimension as u over a characteristic velocity of the flow, which is big U. Okay, so look, in any type of flow, you have characteristic velocity, characteristic lengths. For example, if we take the simple example of a sphere, and you have an upstream flow going towards the sphere, okay, and the sphere has the characteristic length, which is the diameter of the sphere d. So I can say that I can normalize all velocities to the upstream velocity u. So I can say that I can create a variable related to velocity without dimension u star by just dividing the velocity u by the upstream velocity big U. And then I can replace in the equation small u by u star times big U. Okay, so in this case, I can replace, as we said, in this equation u by u star times big U. And for example, if I have, let's say, V, I can define V star is equal to V over U also. So I can normalize all velocities by the upstream velocity BQ. So I can replace here V by V star times U. Okay. And similarly for omega, I can define omega star equals to omega over U. So I can replace in my Navier-Stokes relation, I can replace omega by omega star times U. Okay? So now I am done with scaling velocities. Now I will move to other parameters. What are other parameters present in my equation? I have, for example, lengths x, y, and z. So I should divide them by a length scale to normalize them. Here, for example, in the example of sphere, what is the characteristic length? Is the diameter. So we will say that we can define for any problem a certain length scale, and we can normalize all variables of unit in meter or dimension of length. We can normalize them by L. So I can define a dimensionless parameter x star, which is equal to x over L. And then I can replace in my Navier-Stokes relation, I can replace x by x star times L. Similarly, I replace y by y star times L and z by z star times L. Okay. Now, what about the pressure? Also, we can define a characteristic pressure and normalize with respect to it. Okay. So here, just I am showing you the different dimensionless parameters. We already talked about the velocity normalized parameter. I just have to divide the velocity component by big U to scale, to normalize x and y and z. I can define x star, y star, z star as x over L, y over L, and z over L. Now, if I have, for example, polar coordinates, I can define r star as r over L. Now, I still have parameters in my equation to normalize, which are the time t and the pressure p. Okay. So all variables should be normalized. While constants, I can keep them as they are. And what are the constants here? Gx, rho, mu over rho. So these I will keep them in my equation. These are constant parameters. They are not variables. I just normalize variables. Okay. So now for pressure, look, for pressure, you have several strategies. Some books use P star equal just to a reference pressure or characteristic pressure of the flow over rho u square. And other books use another sophisticated form, which is P star equal to P plus rho gz over rho u square. I will tell you what is the difference and why in some books they use this approach. But at the end, okay, you should know that we can just specify for you use this parameter. You should just know how to use it, okay? And to derive the corresponding dimensionless equations that you will get. So let us start with this definition, and then I will derive for you the expression for the other definition of P, okay? Of P star. So now, for example, after defining all of these parameters, okay, let us find together what will be the form of what will be the resulting normalized form of the equation. So let us start by normalizing this equation. Okay. Just before doing that, we still have the time, the normalized time. For the normalized time, okay, look, we already defined a characteristic velocity and characteristic length of the flow. And you know that time is, we can get it from doing L, okay, because what is the unit here? Unit is second. Okay, if we do L over U, distance over velocity, the dimension for L, it's a length, so it's meter, and the unit for U is meter per second. So when we divide L over U, we get, if you want, the unit of T. This is why if you want to come up with a parameter normalizing, if you want the time, we can say that T, the characteristic time T, if you want, let us call it big T. The characteristic time big T is L over U. So we should scale any time T with respect to L over U. So we can define T star as the time variable over L over U. And when you divide by L over U, you can take U up, which is a numerator, and you get that the normalized time is T times U over L. Okay. Now, once we defined all the normalized factors, parameters, now all we have to do is to replace in our equation each term by the term function of the normalized parameter. Yeah, for example, I will start by del U by del T, okay? I will write del instead of U, I will put U, because we defined U star as U over big U, okay? So I will replace U in the equation by U stars times big U. So I'll get the following. I will get del U star times U, okay, over. Now for del T, what do I obtain? I have del, instead of T, I will put T star times L over U, okay? So I will put, instead of T, T stars times L over U. And you know that L and U are constants because they are characteristic lengths. So I can take them outside of del. Okay. So what will be my resulting first term? The first term will be U square over L times del U star by del T star. Okay. So I can replace del U by del T by the following term. Now, plus U del U by del X. Okay, so again, I replace U by U star times big U times del. Again, I have U again, so del U star times U over del, instead of X, I will put X star times L, X star times L. And again, I can take outside of del U and L. So what do I get? So I will put the final result here. It's plus U square over L. So as you can see, I'm obtaining a common factor, so which is U square over L times U star times del U star by del X star. Now, no need to repeat the procedure for the other terms. You know why? For these two. For these two, you can directly deduce the result. Why? Because they are in the same form of U del U by del X. Just the difference is, instead of V you have V, and instead of X you have Y. So now you can just deduce the form. It will be the same form. So plus u square over L. But instead of u star, since you have v instead of u, you will get v star. So v star times del. Here you have u, so it will remain u star. But now instead of x, you have y, so you replace x star by y star. So del u star by del y star. Okay, and similarly for the last term, you can deduce that it should be in the following form: plus u square over L times w star times del u star by del z star. Okay, so now what you can do, you are done with the first side, you will move to the other side. Okay, equals to, look, now in this definition, when we define p star equal p plus rho gz over rho u square, we consider that z is the vertical axis. So if z is the vertical axis, then g vector is only along z. So you have gx equal to 0. This is what we are considering in this case: gx 0, dy 0, and gz is minus g. Okay, so now what will happen is that gx is 0. I can replace it directly by 0. Now I want to normalize this term. Okay, now as we said, rho is not a variable. We keep it as it is. We normalize p and we normalize x. Okay, so let us normalize p and x. For p, as we said, to be able to replace p, function of p star, from this relation, we can write that p is equal to p star times rho u square minus rho gz minus rho gz. Okay, and now what is nice about this definition, this term is only function of z. So when you do del p by del x, and if you replace p by, when you do del p by del x equal to del of p star times rho u square minus rho gz with respect to x, what will happen is that since z is not function of x, this term, when you derive with respect to x, will cancel out. And since rho and u square are constants, you can take them outside of del. So you can then replace this term by the following: minus 1 over rho times, and of course, instead of x, we'll put x star times L